Hello everyone. Today we are pleased to introduce our paper, MAG, a simple learning-based patient-level aggregation method for detecting microsatellite instability from whole slide images in the IEEE ISBI 2022. I am Kaifeng Pang from Nanjing University. My co-authors are Zuhair Assad, Shilin Zhao, and Yuankai Huo. The prediction of microsatellite instability (MSI) and microsatellite stability (MSS) is essential in predicting both the treatment response and the prognosis of gastrointestinal cancer. Unfortunately, the existing commonly used genetic test-based methods need a high cost so that they are unable to cover all patients who need such a procedure now. In the past few years, deep learning-based algorithms have shown promising results in directly predicting MSI and MSS from hematoxylin and eosin H&E stained whole slide images. These deep learning-based methods can mainly be summarized into two stages. The first stage is using a classification model to do the patch-level prediction in order to get the probability score of each patch. And the second stage is to aggregate patch-level results into patient-level results. However, the major previous innovations and efforts are focused on stage 1, while very few efforts are made for stage 2. So here is the problem we wish to explore: how to integrate the precious patch-level information. This figure shows the details of how to do the prediction of MSS and MSI. After extracting patches from whole slide images, the deep learning classifier is used to get patch-level results. In the following process of aggregating patch-level results, most of previous studies only use the first-order statistics methods. Specifically, Kaiser et al. Calculate the proportion of patches judged to be MSI among all patches as the patient-level probability score. We referred to it as the counting baseline. Yamashita et al. Directly calculate the average probability across all patches as the patient-level probability score. We referred to it as the averaging baseline. As a result, the precious patch-level information from deep learning approaches are not fully utilized in these methods. We hypothesize that a more holistic consideration of patch-level probabilistic distribution using simple machine learning methods, ag SVM, could lead to consistently better patient-level performance of MSI detection. In this paper, we propose a simple but effective patient-level MSI aggregation (MAG) method by modeling overall probabilistic distribution with an SVM classifier. Here is the brief description of our pipeline. Firstly, patches are extracted from the whole slide images of each patient. Then they will be labeled as MSS or MSI so that the training set can be used for the patch-level classification. The convolutional neural network ag ResNet MobileNet is employed to do the patch-level training. After this process, we get the stage 1 patch-level trained classification model. We use this model on patches of the dataset to get probability scores of each patch so that we can convert the whole dataset from patch level to patient level in the next stage. In stage 2, we propose to model the overall distribution of patch level probabilities as the patch level histogram feature. Briefly, the histogram-based features describe the distribution features of the probability scores from all patches within the tumor region. Now let's see how to get the histogram-based features of each patient. Here is an example. This is the histogram of the patches of the patient whose ID number is I. Each histogram has 10 bins as a 10-dimensional array that represents the histogram-based features of the patient. A0 to A9 represents the number of patches within each bin with 0.1 incremental probabilities. Moreover, in order to ensure that all the feature arrays have the same scale, a normalization is conducted to standardize the histograms for different patients. Here is the formula of the normalization. N is the total number of patches for each patient. Let's come back to the pipeline. Now we have used the stage 1 trained model to get the feature arrays in the patient level. Then, we employ machine learning classifier like a broadly validated support vector machine SVM, given the sample size as well as the feature space. The last thing is to do MSI prediction with the stage 1 model and the stage 2 model. After using the stage 1 model to get the feature array of a testing patient, the stage 2 machine learning model can then classify it into either MSI or MSS. In our study, we used the two public datasets acquired from the colorectal cancer TCGA patients CRC dataset and the gastric stomach cancer TCGA patients STAE dataset, respectively. The whole dataset is made up of patches from 644 patients, and all image patches were resized to a fixed size. To evaluate the generalizability of the proposed plug-and-play MAG approach, 5 prevalent models have been used to be the baseline feature extractors. We use the results in prediction and the ground truth labels at the patient level to calculate the F1 score and balanced accuracy BACC score. From the quantitative results, the proposed simple MAG strategy achieved higher F1 scores and balanced accuracy scores than the two commonly used methods, the counting method and the average method, on different models and the two unique datasets. To sum up, we provide a histogram MSI aggregation method in the prediction of microsatellite instability, which is a pipeline that can effectively improve the classification ability of the previous commonly used methods. The improvements are consistent across different patch-level classification models. We hope this pipeline can become a potential routine operation for optimizing the classification model in microsatellite instability prediction, and it can inspire more research on how to make full use of patch-level information. Thank you for your watching. Our code of MAG is released on GitHub.